All right, this is a B tree of order 2 example. So our general rules for a B tree is that the root has from 1 to 2n. So this is n equals 2. That's what we mean by order. So in this case, the root has from 2 to 4, I'm sorry, 1 to 4 keys. And all of the children are going to have 2 to 2n keys, which means they're going to have 2 to 4 keys for this particular order. So that makes sense to you because the roots are formed from, well, the very first node is a root. You have to allow for 1. Also, when the root splits, when a root splits, that value is going to go up 1, and so you have to allow for a root of 1. But the children are never going to have less than 2, because when a child only splits when it's full, and it'll have 4, and that's stable, but then it'll briefly become 5 and then split in half with 2 on one side and 2 on the other, and the middle value going up. So, and keep in mind that in real life, the n's, I'm going to write that down. In real life, n's are way big. Okay, like way big, like a zillion or something. And it may take up a big chunk of a disk drive. They're so darn big, right? They might not even fit, in theory, they might not even fit into memory. And if your secondary storage, your disk drive supports sequential access, then you don't even have to read the entire key into memory. You can just read from the disk until you get to the link that you need to follow, the child link that you need to follow. So these are real small n's, but we just want to understand the concepts here. So we're going to do an insertion sequence of 40, 50, 60, 70, 80, 10, and then just keep on going like that. So we're going to insert 40. So you make a root, and there's nowhere else to go, so you put the 40 there. Then, let's say 50, 60, and 70 come along. They would just go in sorted order, and I'm doing these sorted already just so I don't have to move a bunch of keys around, but you would move keys down as necessary. So, 80 comes along, and you put him here temporarily, and now we need to do a split. So we form a new root, right? And it's going to have 1 in this case. This middle value, 60, is going to go up and occupy the new root. All of these guys are going to be less than 60, and all of these guys are going to be more than 60. So 40 and 50 go in this guy, and the 60 and the 70 go in this guy. I'm sorry, the 70 and the 80 go in this guy. Okay, then let's do 20, 30. So to do 20, you start here, and it's 20 is less than 60, so you follow this link. This is a leaf. By leaf, I mean the bottom, right? The leaves are at the very end of the tree in real trees, right? Same thing. So these are the bottom-most nodes are leaves, and that's where the insertions go. So you put the 20 here. Let me do it over here. So you follow this link, and the 20 is going to go in here. You got to scoot the 40 down. The 20 is going to go here, then the 40, then the 50, right? And if I did 30, the 30 would go in the middle here, right? So now it's time for insert 30. So you follow this link because 30 is less than 60. You start scanning this guy, and 30 is bigger than 20. 30 is less than 40, so the 30 goes here. So it's going to be it's going to be 20, then the 30, then the 40, then the 50, right? And say if we did 55 now, right? You would start here, the 55 would go here. These guys stay the same. So this is 20 so I did 20. Where's it 20? Then I did 30. Now we're doing 55. Yeah. So the 55 hangs out here for a little bit, and that triggers a split because this leaf is overflowing. So the 40 is going to go up to its parent. The 60 is going to have to scoot down, right? 60 scoots down one to make room for the 40, and then this leaf breaks in half. And the 20 and the 30 go in this side, and the 50 and the 55 go in this side. And then this 70-80 node here just stays. And then you gotta scoot the pointers down as appropriate. As you're scooting the keys down, like you scoot 60 down to make room for 40, and you would also scoot the keys, which are, the pointers, which are represented by these arrows. You'd scoot those down as well. So the 20 and the 30 are less than 40. These two guys are in between 40 and 60, and these guys here are all bigger than 60. So let's make this guy split. So I'm going to insert a 56 that would go here, and a 57. That's going to go here, and then a 58. Okay, we'll make this guy split. So I'll do that over here. So insert 56, 57, 58. So right now the root is unchanged. This guy is unchanged, the 20 and the 30. This guy, it's this thing, because the 56, 57, 58 you'd start here. They got to be in between these two guys, so you follow this link. This is a leaf, so that's where they go. So you walk down, the 56 would go here, so 50, 55, 56, right? 57 would go here, the 58 would go here. Let me fix these pointers. So now this guy is overflowed, so that triggers a split. So the middle value goes up to the parent, and this guy's going to break in half. So the parent, okay, we're doing a split now. So the parent, the 56 goes up to its parent. The 40 is still there. The 60 has to scoot down to make room for the 56, and then these leaves here, this one stays the same, this one stays the same, but this one breaks in half, right? So this one stays the same. This one stays the same. This guy breaks in half. And fix the pointers. So this guy broke in half. It has the 50 and the 55. And the 57 and the 58 go in here. All of these guys are in between 40 and 56. All of these guys are in between 56 and 60 in value. All of these guys are bigger than 60 in value. And that's a B tree. Okay, orders of 1, 2, and 3 are good academic exercises to where you can get the rule. You start going to real life where ends are way big, they're too hard to hand execute. But keep in mind that's what's really happening. And the idea, once again, to summarize, is that these keys can be very, very these nodes can be very, very large. They can be distributed throughout the memory architecture that you have. Could be multiple disk drives, many computers. And last thing, the last point is that in real life, you might make something that has some binary tree characteristics, some B tree characteristics. You're going to solve new problems. All right. Thank you.